Welcome to day 7. Homework tonight, we got pages 1 through 4 in our calendar packet. Here's your homework answers. So you can pause here and check your answers. And then like usual, I will go to the worked out solutions and pause for like 10 seconds on each. Feel free to skip over the worked out solutions of any ones that you got correct. So again, go ahead, pause here, check them, and then you can move forward in the video. So 14 was a bit of a tricky one. Our exponent was bigger than the numerator, so first you had to do long division. So that's what's shown there in the top right. And then once you've done the long division, the remainder is something you can do partial fractions with. And the last one, this was an integration by parts because we had a mismatched product. There's no logs, there's no inverse trig, so the polynomial, in other words, monomial, the x is your first thing for you, your dv is secant squared dx. So your uv is x tan x minus your integral of v du, tan x dx. Tan's antiderivative is a negative natural log, absolute value of cos, and then you got your plus c on the end. All right, so we'll be on day 7 in our notes packets, and we're going to look at logistic growth today. So something we've already done this year is exponential growth models. Exponential growth models was when the rate was proportional to the population or the current size of our scenario that we are working with. So we initially saw that as dp over dt over p is equal to k, and then we would multiply that p over and solve our differential equation. Well, we saw eventually that that ended up in the form of ce to the kt, so then we started always just jumping there when going to solve. Now, when t went to infinity, an exponential growth model keeps growing forever. So now our new stuff for today. So in real life, there's not many things that will grow exponentially forever. Oftentimes things will start looking exponential, but will eventually level off. And that's what's called logistic growth. So logistic growth comes up in a lot of real life scenarios. And the one that we are experiencing currently with our pandemic. So if you remember in the spring, they kept talking about the need to flatten the curve. We need to flatten the curve of new cases. That's because the new cases were showing an exponential growth, and by flattening the curve, that would turn it into more of a logistic growth. So that's what was meant by when they kept saying we need to flatten the curve. They wanted it to become logistic as opposed to exponential. Now in logistic growth, the part that's highlighted in green there, our quantity P grows at a rate proportional to itself and to C minus P. So what C minus P represents, C is the carrying capacity. That would be the total population. And then when you do minus P, it's the people that already have something. So if it was like the virus, the people that already have the virus. Another way is the room available for further growth, essentially. So it's who has it, and then times the people that haven't had it yet out of the total population. You can also think of it like with a rumor. So as a rumor spreads, there's some people that have heard it and some people that have not heard it yet. Well, as the rumor continues to spread, there are fewer people left that have not heard it yet, and that's why it starts to level off. In a pandemic sense, there's fewer people to contract the virus, so that's why it starts to level off. All right, so let's say we had the phrase the rate of change in P is proportional to both itself and C minus P. Well, let's start it off with dP over dt. If it's proportional, that means it's divided by P times C minus P, and that should equal some value K, some constant K. So that's how it initially starts out, but then if we multiply that over, our rate is really equal to K times P times C minus P. When we see something in this form, that is our differential that represents logistic growth. So our goal is to solve the differential equation. And first thing we're going to do is we're going to separate our variables. So we're going to bring it back with the P and the C minus P over to the other side. But I'm going to write it as 1 over P times C minus P, and then dP. And that's going to equal K times dt. And where that's coming from, so multiplied the dt over with the K, divided the P and the C minus P over with the dP. Because P is kind of like our Y value, and T is kind of like our X value. So next thing we're going to do is we're going to use partial fractions on this side. So we've got 1 over P times C minus P. And we're going to split that up into A over P plus B over C minus P. When we multiply through by our denominator on the left, we're going to get 1 equals A times C minus P plus BP. One strategic thing to let P equal would be 0. When we do that, the second term wipes out, and we get 1 equals AC, or in other words, A is equal to 1 over C. Another strategic thing we can let P equal would be C. So we would get 1 equals C minus C is 0, so the first term is wiped out. So we would just have BC. If we divide the C over, we get B also happens to be 1 over C. So basically, this is what we have now. Our A and B were identical. They were both 1 over C. We've split those up, and we still have the equals K dt on the other side. So we can really pull out the 1 over C. And now in step 3, we're just going to integrate each side. So I'm going to write it as 1 over C, the integral of 1 over P dP, plus 1 over C, the integral 1 over C minus P dP, equals the integral of K dt. Well, the first one, remember, P is our variable, not the C. C is our carrying capacity, some constant. So we're going to have 1 over C, natural log absolute value of P. Now over here, technically we would have to do a little U substitution. So we'd have U equals C minus P. du would equal minus dP. So we'd have to correct, we'd have minus 1 du is equal to dP. So because of the minus 1, when we do this antiderivative, we're going to end up with minus 1 over C natural log absolute value of c minus p. And where that's coming from is because we would have natural log absolute value of u, and then we replace the u with c minus p. T is our variable over on the right, so we'll just have kt plus, and we have to do our constant. Normally we do plus c, but c is representing our carrying capacity, that spot where it's leveling off, the total population. So we've got to pick a different letter. Let's just pick D for our other letter. So now in step 4, we're going to solve this. So where we're at right now, again, we have 1 over c natural log absolute value of p minus 1 over c natural log absolute value of c minus p equals kt plus d. So we're going to do two things at once. Let's multiply the c out of there. So over on the right, we're going to have c kt. And the c, which is some constant, times the d, which is some constant, is still just going to be some constant. So let's just still call it d for now, because it's some constant value. Okay, it's c times d, but it'll still just be some constant. Over on the left, we'll have subtraction with our logs. So we can write this as natural log absolute value of p over absolute value of c minus p. Well, we're dealing with a real life scenario. So our P is like the population that already knows the rumor or the population that already has the virus. So that's got to be a positive value. C represents that total population, that carrying capacity. So that's got to be bigger than the people that already know it. So C minus P also has to be positive. So because of that, we know both things will be positive, so we can drop the absolute value bars. Well, we can switch this to an exponential. So P over C minus P is equal to E to the C K T plus D. And this is where we've got to get a little creative. If I had, and you don't have to write this thing right now, if we have 1/2 equals 2/4, hopefully you agree that's a true statement. We could also flip both fractions, so 2 over 1 equals 4 over 2, and that's also still a true statement. So we're going to do that idea right now. So we're going to flip the P over C minus P to C minus P over P. And if we flip the other fraction, it's going to be 1 over that, so it's really just negating the exponent. So we could write it as e to the negative ct, and then we'd have to negate the d, but negating the constant is still just some other constant, so let's just leave it as d for right now. The whole reason for doing that is now on the left we can divide them each individually by p. So we'll have c over p minus 1 is equal to e to the minus ckt plus d. We can add the 1 over, so that's c over p is equal to e to the minus ckt plus d, and then at the end we'll have a plus 1. And we're trying to solve for p, so we're going to redo that idea where we flip both fractions. So this is going to be p over c now. We can't just do the negative exponent this time because we've got the plus 1 on the end. So this time we've got to write it as 1 over e to the minus ckt plus d, and then plus 1 on the end. And to finish getting p alone, we need to multiply the c over. So we'll have p equals, c will be on top. And then don't write the bottom yet, I want to walk you through something. If you have e to the x plus 2, you don't have to write that little bit on that I'm writing right now. That's the same as saying e to the x times e to the second. Because when you multiply things, you add the exponents. So if we have e to the minus ckt plus d, that's the same as saying e to the minus ckt times e to the d. Well, e to the d is just some other constant. So we can just pick a letter to represent that. the one you often see is little b. So we're going to rewrite that e to the minus ckt plus d as just little b times e to the minus ckt, and then plus 1 on the end. And that's it. That's our logistic model solved for p. Now, I would suggest memorizing that because you're not going to want to have to do that derivation every single time. It's a little messy. There's some little tricks in there. So you're probably just going to want to memorize that. So down in the box, so in general, we have, if you have a logistic differential equation, our solution to that is going to be the carrying capacity over some constant little b times e raised to minus the carrying capacity times some constant k, which was in the differential equation, t, and then a plus 1 at the end. And that's where k and b and c, k and b are constants, and c represents the carrying capacity, that total population. Now that we know that, let's see if we can apply it in an example. So we've got FM High School, let's say it has 1,650 students. Mrs. Kushner has an AP Calc group of 50 students. She abuses and humiliates them on a regular basis. Because of this, all the AP Calc students start a rumor within the school that Mrs. Kushner is definitely going to win Meanest Teacher in the school award. After one day, 150 students have already heard the rumor. So we want to write a differential equation to model this situation. Well, our differential equation, when we've got anything that's in logistic form, so a rumor spreading is something that would be in logistic form, we'll have dp over dt. And remember, our basic setup is k, p, and then times the carrying capacity minus p. Well, of those things, right now, the only one that we know is the carrying capacity. There's 1,650 total students, so we can fill in that value of c. And based on what we just saw on the previous slide, our solution to that differential equation should be the carrying capacity on top over some constant little b, e, minus that carrying capacity, some constant k, t, and then plus 1. So in that equation, we currently have two constants we need to solve for. Conveniently, we know 2 points in the question. At time 0, 50 students should know the rumor because there was 50 students in the class. And after one day, 150 students knew the rumor. So we have 2 points so that we can find the two different constants. Use the one that's easier to start. So we're going to use the 0, 50. So we're going to have 50 equals, we'll have 1650 over, if we put 0 in for t, that's going to make e's exponent all be 0. E to the 0 is 1, so we just get b plus 1. We can multiply the b plus 1 over, so that'll be 50 times b plus 1 equals 1650. I would say don't even bother distributing it and just divide the 50 over. So this will be b plus 1. If you divide that, we'll get 33. Subtract the 1, and we'll get b is 32. So we now know that this is p of t equals 1650 over 32 e to the minus 1650 kt plus 1. Well, now let's use the other point, 1 comma 150. So 150 will go here. We'll have 1650 over 32 e. If we put the 1 in for t, this will just give us minus 1650k up here, and then plus 1. So similar idea, we are going to multiply the denominator over. I would suggest not distributing it. We can divide the 150 over, and that's going to give us 11 equals 32e to the minus 1650 k plus 1. If we subtract the 1 over, we'll get 10, and divide the 32 over, we'll get 10 over 32, or that could be reduced to 5/16. So again, subtract the 1, divide by 32, and we'll have e to the negative 1650k equals 5/16. Well, we'll switch this to a natural log, so negative 1650k equals natural log of 5/16. And divide the negative 1650 over, so k we're going to write as negative 1 over 1650, natural log of 5/16. So putting it all together, our P of t equation, our carrying capacity was 1650. Our little b value was 32. We have E. Now, when we do our minus our carrying capacity, so minus 1650, times our K and then T, the minuses end up wiping each other out. The 1650 times the 1 over 1650 are going to wipe each other out. So we're just going to have natural log of 5/16 T. And then we got the plus 1 on the end also. K rarely works out pretty. Okay? It's going to be something messy in most cases. So that's our solution to that differential equation given the 2 points. So we've kind of done all those steps there and there. Sorry, I kind of put them all on the same page. So if we graph this now, so we got the 1650 over 32e. We've got the natural log of the 5 over 16. Instead of t, we got to put x in. And make sure you're out of the exponent when you do your plus 1. So we're going to change this value. Our carrying capacity was 1650, so I'm just going to put in 2000. And let's put like 20 in there, I guess. So that does, in fact, look logistic. If you do a control T, we've got 150, and we've got the 0, 50 as points there. So we're in good shape there. So now they wanted to know how many students knew the rumor at 6 days. Well, we can just look at our T-chart here. And at 6 days, we have, to the nearest student, we have 1,602 students. So we'd have P of 6 equals 1,602 students. So next one, when is the rumor growing the fastest? You'll probably want to write kind of small here because we will have a bunch of work. So if we want to know when the rumor's going the fastest, we want to know when is the maximum of our differential equation. Well, remember our differential equation was dp over dt is equal to kp times 1650 minus p. And we know what k is but you'll see that we're not going to need to fill in the ugly value for k. So we'll just leave it as k for right now. So if we want to know when the maximum of that rate is, we'll define the maximum of something. You've got to look at its derivative, so at the next derivative. So to do the second derivative, we'll have d2p over dt squared. And we've got to do a product rule, and we are doing the derivative with respect to t of our variable p. So the derivative of kp, we got to do a product rule here, will be k times the regular 1650 minus p times dp over dt. And you can either put that dp over dt at the end, or you can put it right with the k, which is where we took the derivative of it. And then we're going to do plus, we'll have regular kp times the derivative of that parenthesis part, which would just be -1 times dp over dt. I'm going to move up here, so that's d2p over dt squared. We can pull the dp over dt out. And I'm also going to distribute the k. So we're going to have a dp over dt. Distribute the k, we'll have 1650k minus kp, then minus the other kp. So I guess we can actually just right now, let's make that minus 2kp. And then we can refill in for dp over dt, because we know from the beginning that that was kp times 1650 minus p, and then we've got the other part. So we've got 1650k minus 2kp. And now we'll set that derivative equal to 0. So if we do kp equals 0, we're going to get p equals 0. If we do 1650 minus p equals 0, we'll get p equals 1650. And if we set this one equal to 0, if we add the 2kp over to the right and then divide by 2k, we're going to get 825 is equal to p. So the things we're going to put on our number line, this is our d2p over dt squared, and these are values of p down here. We'll have 0, 825, and 1650. Now we don't have to go left of 0 and right of 1650 because your population can't be negative, and our carrying capacity was 1650. You can't go above the total number. So if you have something like, say, 1, you're going to get a positive in the first part because k times 1. You'll get a positive in the second part, and you'll get a positive in the last part, so you'll get plus. But if you did something like 900, now suddenly this one is going to become negative. So you'll have a plus followed by a minus. So we're going to have a max at 825 is equal to p, since d2p over dt squared switches from positive to negative. And you might be asking why is it a max when the second derivative is switching? Well, it's because we are trying to find when is it growing the fastest. So we want the maximum of the rate, so it's always its next derivative. Well, the question said, when is the rumor going the fastest? We found the population when it is going the fastest. So all we're going to do is we're going to go back to our graph. and hit tab, and we're going to graph that 825. And we'll just now find the intersection. So you got menu, analyze, graph, intersection. We'll go left of it, we'll go right of it, and we've got 2.98. Let's see if it'll allow, there we go, we need some more. Remember, you can click the X value and hit plus, and it'll show you more spots. So to 3 decimal places, that would be 2.980 days. Okay, and this is all for the question up above, part D. Sorry, I didn't give you a ton of space. So we want to know, what is the maximum rate at which the rumor spreads at? Well, we know the maximum rate is going to occur at 2.980. There's a couple of ways to do that. We can go back to our rate equation, so our dp over dt, and we can just fill everything in if we want. We can fill in our k, the minus 1 over 1650, natural log of 5/16. We know our p that we want is the 825, and then times 1650 minus 825. Because we know the maximum rate occurred when p was 825. So you can punch that in and you get 479.800 students per day. And that's one option. Or we want the rate of the original function at 2.980. So another way we could do it is if we go to the graph, and I would say keep it out to as many decimal places as you can. So let's do 2.9796. But we're going to go menu, analyze graph. We'll do the derivative. We want to do the logistic function. And we've got 2.9796. 2.9796. If we hit enter, I'm not sure if it will allow me to drag that on the smartboard. And if we extend the decimals out, notice that matches. We got 479.800. So doing it on the calculator, that might be the quicker way to find it, but you also you could sub it everything into the differential equation. So the big thing for today is knowing the basic setup of your solution to the logistic differential equation, being able to sub in the 2 points to find the constants, and then just being able to answer follow-up questions from that. That's it for this video. Have a great rest of your day.